Okay, so we've got a cylinder, and I already drew the diagram because it's always good when you're doing these problems to visualize what's happening. My cylinder has a linear charge density. It's positive, and it has a uniform charge distribution. So there's positive charges all throughout. It says it's a very long cylinder, and we're really analyzing the electric field at a distance r less than big R. And so I know right off the bat that the electric field lines that I'm concerned about are the ones that are coming up and out of the sides of the cylinder, not the ends of the cylinder. And so I'm going to analyze the curved edge of my cylinder rather than the endpoints. That's the area that I'm going to plug into my Gaussian surface. So let me just clear out, whoops, that's the wrong one, all these lines here and start writing my Gaussian expression. And I have decided that I want the area of the curved part, which is 2 pi r L. And again, L is just this distance here. I have decided that's how short I want my cylinder to be. It's just a constant. Okay, now we need to figure out what's the charge enclosed. The charge enclosed is actually distributed over this volume. So what I want is every charge inside that smaller cylinder. The problem is I don't have volume density, I have linear density, which is charge over length. And let me use a lowercase l again for length. So the charge that I have is lambda L, and lambda L doesn't take into consideration smaller radiuses. It only takes into consideration the length of that cylinder. So really, what I've been given here is this Q, within this entire area here. Now, I don't want all of that charge. I only want a fraction of that charge. Well, because we know that it's uniform distribution, I know that if I were to take a fraction of the volume, which for a cylinder is pi little r squared L, over the full volume, which is pi big R squared L, so that's the volume in green, and then this is the volume in yellow. If I can get a fraction of that smaller volume over the bigger volume, that'll be the same as the fraction of my charge enclosed over the charge enclosed in this green cylinder. So by simplifying this down, I know that the smaller volume over the bigger volume has a ratio of r squared over big R squared. This is the volume ratio. And again, that volume ratio is going to be the same as the charge ratio because of uniform charge distribution. So this is my charge in green, lambda L. If I just want what's enclosed, I can take my volume ratio and multiply that by the bigger charge we have here, and that will give me the charge enclosed. So if I were to plug that in here, that would just give me the smaller yellow enclosed charge. So I'm going to plug that in. E is 2 pi r L. My Q enclosed for this small area is going to be lambda L r squared over big R squared times epsilon naught. We have a few equations or variables that end up canceling, but not a ton. And then I'm going to isolate the electric field to get lambda r over 2 pi epsilon naught big R squared. And the answer in the key here would be C.